Today we're going to work on an advanced player controller that is an amalgamation of various controllers that I've studied over the last few years, as well as code that we've written on this channel previously. In this video, we're going to tackle all the physics involved to handle step height, friction, gravity, slopes, and jumping and falling. We'll follow this one up next week with custom camera controls for orbiting and detecting obstacles, and a few extras like animations. There will be a lot of vector math today, and I've included a library of helpful methods to make things a bit easier. Now, some of the code and calculations today will be advanced. The code is available for you in the repository for reference, but a good understanding of how it works is essential to be able to adapt this to your own projects. So with that said, let's start building an advanced player controller. I want to start writing code today with a Raycast Sensor class. Now we want to make it a little bit generic so that we can use it to detect things like walls and so on in the future, but its main purpose today is going to be to detect the ground. We need two public fields here. One will be the cast length. This will determine how far away the ray will be cast in the game world. Then we need a layer mask. For now, let's initialize it with a value of 255. Let's have some private fields here so that we can store the origin of the ray and the transform that it's associated with. That's going to be the transform of our player. Let's also make a public enum here so that we could, in the future, perhaps cast this in a different direction than downwards. And we can store that in another private field. And finally, if we hit anything with our ray, let's store that information in a Raycast hit variable. To initialize this class, let's have a constructor that takes in the player's transform, and then we'll set that field. So the main purpose of this class is to actually cast a ray and see if we hit something. So let's make a public method here, cast. We're going to need two vectors here, the origin in the world. To get the world origin from the transform, we can use the method transform point. We're also going to want to know the world direction that we want to shoot the ray in. To do that, we'll have another method that'll translate our enum into an actual direction. So all we really need to do for this is create a new method, get cast direction, and based on the value we have in our cast direction, we'll just have a switch expression here that returns the correct direction. While we're at it, we might as well create a public setter here for the cast direction. Okay, well, let's wrap this up here by doing an actual physics raycast. Let's come back up into the cast method. We know the origin, we know the direction. Let's just cast the ray and see if we get anything out into our hit info variable. I'm going to add query trigger interaction.ignore here because I don't really want to be casting into any triggers. So this is a very simple class, but let's make it slightly more useful by adding a setter for the cast origin. We'll use the inverse transform point method to convert a world space position into the local space of the transform that we've stored. Now let's make a few more public methods just for utility. Have we actually hit something? We'd know that if the collider was not null. We can get the distance to that hit. We can get its normal. We can get its position, its collider, and its transform. Now remember that a Raycast hit is a value object, so it can never be null, but some of the things inside of it could be null. So the collider could be null if nothing was hit. Okay, and that's it. Now we've got ourselves a pretty straightforward Raycast sensor. Of course, you can elaborate on this to make a sphere cast sensor if you want, or maybe even a sensor that has multiple Raycasts in it. But this is all we need for this player controller. We're going to work on the player mover class next. Its main purpose is to allow us to move along the ground smoothly, including going over stairs and over terrains. So this has a public field here, step height ratio. This will allow us to adjust how much room there is between the ground and the collider, giving us a little bit of room to get over stairs, get over little bumps. And based on that value, we'll be able to recalculate our collider dimensions and all the settings related to our sensor. Let's start this class off by requiring a few components. We need a Rigidbody and a capsule collider to make this work, and then we can define some settings. Let's start with that step height ratio. I'm going to start it with a 0.1, but I know already that 0.1 is too small even for some of the stairs in my demo scene. And that's why it's nice to have this adjustable. You never know what you're going to put in your game world that you're going to need your player to climb over. Let's also include all the fields that are going to define our collider. So that's height, thickness, and offset. After that, we can define the fields that we want to store that are related to this. So that's the Rigidbody, the transform of our player, this capsule collider that's on this game object, and of course our Raycast sensor. Beyond this, we're going to need some private variables to keep track of the state of things within this class. For starters, I want to know if we're grounded or not. Secondly, we need a base sensor range. This will be recalibrated anytime we change the step height. We're going to use a current ground adjustment velocity to smoothly move the player up or down if they're going over some kind of bump. And let's keep track of the layer that's currently assigned to this game object. Just a few more settings to add here. Let's expose a Boolean here so we can toggle some kind of debug mode. We may want to be drawing lines for our sensor. On top of that, we're going to have a flag to say that we're going to extend the sensor a little bit. In case it's uneven ground, we're going to want to look just a little bit further than the base range. I'm just going to paste in a few inline comments. And I was thinking, because there's so many variables here and it's taking up a lot of screen real estate for this video, I'm just going to wrap this up in a region and then collapse it. There's going to be three main parts to this class, so why don't we set up some methods for ourselves. In Awake, we're going to do some setup and recalibrate those collider settings. We also want to do that in onValidate because we want to do it in the editor. And the main purpose of this class is to check the ground using the sensor and adjust all of these little settings for ourselves so that we can smoothly move across the ground. So we can break the Awake method down into setup and the recalculation of collider dimensions. We could also use the onValidate method to say, if this is the active game object in the hierarchy, let's also recalibrate those collider dimensions every time the onValidate method runs. Let's come down a little bit and start with the setup method. We can use this to assign the transform. We can get a reference to our Rigidbody and to our capsule collider. And then with our Rigidbody, let's make sure we freeze the rotations and turn off use gravity because we're going to control these things on our own. Okay, let's collapse that up and scroll down a little bit for some room. Let's work on recalibrating the collider based on the step height. If our collider is set to null, that means we're in editor mode and setup hasn't been run yet. So let's do that. Let's start with the height. We can get the correct collider height by multiplying it by 1 minus the step height ratio. We can get the correct radius by dividing the collider thickness variable in half. Then we can figure out the collider center by multiplying the offset by the collider height plus a new vector where the y value is the step height ratio multiplied by the height divided in half. Now let's have a little safety check here just to make sure that the collider's radius does not exceed half of its height. This will maintain a valid capsule shape and prevent potential overlap issues. If we've gone beyond that threshold, let's just set the radius equals to half of the height. So now we've changed all the properties of the collider. We should recalibrate the sensor too, but let's do that in a separate method. I'll put this under the setup method just so we don't have to keep scrolling. Let's start by using the null coalescing assignment operator to make sure that we actually have a sensor. Then we can use the public methods on the sensor class to set the cast origin, which is the center of the collider, and set the cast direction, which we already know is going to be down in this case. Next, we can recalculate the sensor layer mask just in case anything has changed in that regard. We'll get to that in a minute. Let's finish this method up first. We're going to want to add a small float, a safety distance factor. This will just be a small number that we'll use to prevent clipping issues. So we're going to want to figure out how far to cast the ray. This is essentially going to be how much we've adjusted the collider height and incorporate that step height ratio. Then we can update the base sensor range to incorporate the length, the safety distance factor, and we can multiply that by the local scale. The sensor's cast length, we're going to update at runtime. Let's just set it to a basic default value. But when it comes to recalculating this sensor layer mask, first let's make sure we have a reference to this game object's layer. Then let's start working on what the mask is actually going to be. Let's start with an initial value of physics.allLayers. This is a constant that is equal to -1, which represents all 32 bits being set to 1 in a 32-bit integer. Now we can iterate over all 32 layers and use Unity's collision matrix settings to determine whether or not this object layer is set to ignore layer I. And if it is, we'll use bit shifting to turn that off in the layer mask. Beyond that, we should figure out which layer is the ignore raycast layer, and we should clear that bit in the layer mask as well. Let's make sure we assign this to our sensor's layer mask field. And let's also make sure that we update our current layer to be the layer we were just working on there, which is the layer of this game object. Well, that was a lot of coding. Why don't we go look at the results of our efforts? I haven't actually done any setup here, so let's make a new game object for our hero, and I'm going to start laying out the game objects we need here. I'm going to put 2 empty game objects under the hero. One is model root, and under the model root, I'm going to drag in my actual model here, and I'm going to have to reset a few things, so I'm just going to use the better transforms reset. Make sure we're right at 0 here. Perfect. Okay, we need another child, and that is going to be for the camera root. The camera root sits at the same level as the model root, but underneath there, we're going to have several children. This is because we're going to build a camera that can orbit the player. So I need it to be independent of everything that's going on with the model. So we're going to have controls, we're going to have a target, and then right under there, I'm going to add an actual camera. Now, having these multiple layers is going to allow us to adjust the camera based on obstacles in the world and still be able to rotate independently of the model. But let's not worry about the camera for now. Let's just come back to the hero and let's add our player mover script to it. I'm going to expand the player mover component and the capsule collider component because I want you to be able to see in real time how onValidate is going to adjust the collider based on settings in the mover. Now, I know this model's height is roughly 1.5 and should be offset by about 0.5. Let me turn off the gizmo icons here so we can see. Now, if I start adjusting the step height ratio, you can see our collider is going to be adjusted in real time. And the same thing applies for any of those other public settings on the player mover. They're all going to adjust our collider for us. We really don't have to touch the collider at all. Okay, why don't we get down to the business of what this player mover class is really all about, which is checking for the ground and making sure that we adjust ourselves properly. We're going to be calling this at the beginning of every fixed update. So first, let's make sure that our current layer is the same as what our game objects layer actually is. If it's not, let's recalculate the sensor layer mask. The vector that we're going to use to smoothly move ourselves up and down over bumps in the road, let's initialize that at vector 3.0. Let's also set our sensor's cast length here. So if the isUsingExtendedSensorRange Boolean is true, then let's set it to be the base sensor range plus the collider height multiplied by the local scale and multiplied by the step height ratio. If we're not using the extended sensor range, then we just have to set it to be the base sensor range that we calculated earlier. Then we can call the sensor's cast method. This will capture the Raycast hit, and now we'll know if we're actually touching the ground or not. So if we're not touching the ground, let's just get out of here. Nothing left to do. But if we are, we want to make some adjustments for that smooth movement. Let's start by getting the distance to the ground from the sensor. Next, we calculate the upper limit, which is half the collider's height above the step area. So this will represent the top boundary of where the player should ideally be positioned, accounting for any scaling applied to the player's size. Then we can determine a middle point, which is where we want the player's feet to be relative to the ground. So this point takes into account both the upper part and the step height of the collider. Then we can figure out the distance to go, which is the difference between where the player currently is and where they should be, the middle. Finally, we can calculate the actual current ground adjustment velocity, which is the velocity needed to move the player to the correct position over the course of a single frame. So now that we've calculated that vector, let's create another public method here so that we can pass in the velocity that we actually want to move the player at. We can combine that velocity with the current ground adjustment velocity, and that's what we're going to apply to our Rigidbody's linear velocity to make sure that we get that smooth movement. We're going to set that from the player controller and a few other things. Let's make a public method so that we can set the extended sensor range if we want. Let's also make a few getter methods here so we know that if we're grounded or not, and we might also want to get the ground normal. And that's it. We're all done with the player mover class. So we're not going to be able to test that player mover class very well until we build at least part of our player controller. The primary purpose of this class is to calculate momentum and velocity based on player input and the state that we're in, and then feed that into the player mover. So let's start by defining some class members that'll hold all this information for us. The first one is going to be an input reader scriptable object. Now, this is something we built back in the 3D platformer video. I'll have a link to that on the screen. And just want to take a really quick look at it because we don't need much from it actually at this point anyway. We just need to be able to get the direction. And when we get to the camera, we're going to need the look direction. These are both properties of the object. I'm going to use Odin's required attribute here just to make sure that we fill that out or get a warning if we don't, because we're going to need it. Now let's get some references to things we need. The transform of the player mover we're going to be using, a ceiling detector, which is going to be optional. We're going to want to remember the state of our jump input. We're going to get to jumping towards the end of the video. Okay, let's make this as configurable as possible with some public members. Movement speed, of course, is the most important one. We're going to want an air control rate. This will affect how much control the player has when they're in the air. We're going to want a jump speed, how much force is applied when we jump, how long we can jump for, air friction while we're airborne, ground friction when we're on the ground, gravity that we're going to apply every frame, slide gravity when we're sliding down a slope, slope limit, which means the max incline we can go up, We're going to optionally use local momentum if we want, which means local to our transform and not the world. Now, we're also going to depend on two things that we've built previously on this channel. One is a state machine. The other is going to be an improved timer, a countdown timer. I'm going to put links to both of those things on the screen and in the description of the video if you're not familiar with those. Eventually, when we get the camera set up, we're going to be able to control the movement based on the direction that the camera is pointing. Let's get a reference to that. Let's have a few vector 3s here that we can store our physics calculations in after every fixed update. So that'll be our momentum, our saved velocity, which is our velocity affected by momentum and other forces, and our saved movement velocity will be our velocity based on player input. Finally, let's add two public actions here that we can fire off when we jump and when we come back down to Earth. These will be mostly useful for animations and effects. Okay, that's a lot of class members, so I got smart this time and wrapped it up in a region. We'll just collapse that up and start working on our logic. Our awake method is going to be pretty straightforward. Let's get a shorthand reference to the transform. Let's get a reference to the player mover component, and let's make sure that we require that as well. And then let's optionally get a reference to the ceiling detector. Let's set up a jump timer. That'll be a new countdown timer of time jump duration. The last part of the awake method is going to be to set up the state machine, but we're going to get to that later after we've handled momentum. So being able to calculate momentum is the primary purpose of this player controller, based on gravity, based on player input, and all kinds of other factors. So we're going to have a public method here so that at any time we're able to get the momentum out. And if we're using local momentum, all we have to do is multiply the momentum by the transform's local to world matrix. So we're going to be doing that multiple times through here, just so we have the option to use local or world. Now, the core of the logic is going to happen in fixed update. And the first part of that is going to be to ask our mover to check for ground. After the ground check, we're going to handle momentum, and we can do that in a separate method. And once we've figured out momentum, then we can actually figure out the velocity we want to apply to the rigid body. So let's come down here a little bit and define our handle momentum method. Now, the first thing we want to do inside the method is take our existing momentum, and if we're going to use local momentum, we need to multiply it by that local to world matrix again. Now we can separate the vertical momentum from the horizontal momentum. To get the vertical momentum, I'm going to use a helper method, extract.vector, from this vector math class. This will pull out just the up portion of that vector. Let's take a look at it quickly. It's very simple. Just normalize the direction and then multiply the direction by vector 3 dot, and then we'll pass in vector and direction. That'll give us just that one component of the vector. This vector math class is a class that I'm going to add to Unity utils eventually after I add some more methods to it. I'll include it with the source code for this video as well. So now that we have the vertical momentum, we can actually get the horizontal momentum just by taking momentum and subtracting the vertical momentum portion of it. Okay, with those two things split up, let's handle gravity. We'll apply a gravity force multiplied by time.delta time to the vertical momentum, but let's add a check here. If we're in the grounded state and we're still applying a negative force to our vertical momentum, let's set it to 0 because we don't want to push our player down into the ground or continually have a negative pushing down force on them. Okay, next step, we want to check if we're not on the ground. Then we're going to need to take some special considerations for how we're going to handle it. Let's scroll down here a little bit. In the context of our player controller, after we've defined our states, we're going to be able to say that we are grounded if we're either in the grounded state or the sliding state. Now, because we're not going to be defining the state machine for a minute or two, I'm just going to bring up the actual states and put them on the screen here so you can have an idea of what we're going to be going for. We'll be able to use the states to make these kind of logical decisions. So if we're not on the ground, what are we going to do? Well, we're going to have to figure out what our actual movement velocity is and then make some adjustments to it. Let's start making some helper methods. The first one is going to be calculate movement velocity. This essentially is our movement direction multiplied by our movement speed. Let's have a separate method to calculate the movement direction that'll be based on whether or not we have a camera and the player's input. So let's first suppose that we haven't supplied a camera transform to this. In that case, we just want direct input, and we can do that with the input reader's direction property. That supplies us the vector 2 that we can multiply by tr.right and tr.forward. Combine those two together, and we've got our direction. But if we did supply a camera to this component, then we're going to use vector 3.project_on_plane. This will let us figure out what direction we should actually be moving in based on the direction that the camera is pointing in and not the direction that the player is facing. Now that we have a direction, let's figure out if the magnitude is greater than 1. If so, send back direction.normalized, otherwise just a direction. Okay, that's enough of this sidebar. Let's get back to handling our airborne movement. I have to scroll down a little bit here. Okay, let's start this off by checking if our horizontal momentum's magnitude is greater than the movement speed. This could have accumulated from a fall or a jump or something. If that's the case, first let's evaluate whether or not the movement velocity vector has any component in the direction of the current momentum. We can do this by using the dot product to make sure that we're not accelerating in the same direction. If so, we'll remove the overlapping component from the movement velocity using the vectormath.remove.vector method. After this, we can add the modified movement velocity to the horizontal momentum scaled down by a factor of 0.25. This will provide subtle air control without overwhelming the existing momentum. On the other hand, if the horizontal momentum is within range of our movement speed, we can just directly add the movement velocity to the momentum and scale that by our air control rate. Finally, let's use vector3.clamp magnitude to make sure that the momentum does not exceed our movement speed. This will maintain control and consistency in our movement while we're in the air. Well, that's a lot of logic to have nested down into 3 if statements there. Let's bring this out into its own method. We'll call it adjust horizontal momentum. I'm just going to cut that out, paste it into here, and then where we had this logic before in our one if statement, let's just call out to that method using a ref for horizontal momentum. And actually we can inline this movement velocity. It doesn't need to be its own separate local variable there. Okay, we're done with handling airborne movement. Let's collapse up that method and move on because we need to think about what we're going to do when we're sliding. So let's have another if statement. If our state machine is in the sliding state, let's have another method. We'll call it handle sliding. Again, we'll use a ref to pass in the horizontal momentum. So let's define this method right below. So we'll start by calculating the point down vector. This is going to represent the direction of the slope by projecting the ground's normal vector onto the plane perpendicular to the vertical up vector. This will give us the direction in which the slope descends. Then let's get the player's movement velocity, and we're going to remove the point down vector from that value. This is going to make sure that our player does not accelerate excessively down the slope due to player input. Now we can adjust the horizontal momentum by adding the movement velocity multiplied by time.fixed delta time. Next, let's project the entire momentum vector onto the plane that's defined by the ground normal. This will make sure that the player slides along the slope without being influenced by any irregularities. Then, if there's any upward momentum, let's remove it. We'll check the dot product of the momentum with the upward vector, and we'll remove anything that's positive. Finally, let's calculate the slide direction by projecting the downward up vector onto the ground plane. This is going to give us the direction the player should slide downwards. We can then adjust the momentum by adding this slide direction scaled by our slide gravity and time.delta time. This will simulate the effect of gravity pulling the player down the slope and give us something that's smooth and realistic. Okay, let's collapse that up and move on. Next, let's handle friction. If we're in the grounded state, we're going to use our ground friction value. Otherwise, we'll use the air friction one. And what we'll do is we'll update the horizontal momentum by using the vector3 move towards method. We'll pass in horizontal momentum, vector3.0, and our friction multiplied by time.delta time. Now, finally, at this point, we're able to calculate our actual momentum by combining horizontal momentum with vertical momentum. Towards the end of the video, we're going to handle jumping, so we'll come back to this. But we're all finished for handling momentum, so we can again check our use local momentum variable, and if necessary, we will convert this back to world space. So now we're done handling momentum other than jumping. So what I'm going to do is collapse up this method, and we're going to come back to our fixed update method where we had left one comment there. I'm actually going to collapse down this calculate movement direction method as well. We don't need that. So in our fixed update method, there's not very much left to do. Let's actually remove this comment. Now to calculate the velocity, we already created a method, calculate movement velocity, but that only really applies when we're on the ground and not in the air. So we'll only use that if we're in the grounded state, otherwise vector3.0. But we want to add our momentum to our velocity. So again, we'll use our Boolean use local momentum. If that's true, we're going to use the local to world matrix. Otherwise, we'll just add the momentum. Now let's tell our mover to use the extended sensor range if we're on the ground. Let's also tell it to set the velocity based on the velocity we just calculated and its own internal calculations. Then let's just save a few values for the next frame. We can save our saved velocity will just be the velocity value. The saved movement velocity will be the one we calculated based on user input. Okay, that's really everything we're going to do with fixed update for now until we come back to jumping, which will be minor. Let's create a start method here because as soon as the player controller starts up, I want to enable the player actions. The other thing we want to take care of is our state machine. I'm going to scroll down here to give us maximum screen real estate, and we'll start a new method. So the state machine we're going to use is exactly or almost exactly the same as the one used in the 3D platformer project. I'll put a link to that video on the screen. So with that in mind, I'm not going to go into detail on the inner workings of this state machine here. Let's initialize a new state machine and then declare and initialize 5 new states: grounded, falling, sliding, rising, and jumping. We'll define 2 helper methods here. The first one is going to be at. When we're at one state, we want to go to another state and the condition it depends on. The other one will be any, and this is when we want to transition to a state from any other state based on a condition. We can also set up some conditions so that when we're defining the transitions of our state machine, it'll be a little less verbose. Is rising is when the dot product of our momentum versus transform dot up is greater than 0. Falling is the inverse of that, less than 0. We could have another one to figure out when we're going to slide, and that's when the angle between our ground normal and tr dot up is greater than the slope limit. So let's define a bunch of these state transitions. Let's start when we're on the ground. If we're going from grounded to rising, the condition is we must be rising. If we're at grounded to sliding, means that we're on the ground and the ground is too steep. If we're grounded to falling, it means that we're not on the ground at all. From grounded to jumping means that either the jump key is being pressed or it was just pressed and the input is not locked. We're going to get to jumping in just a few minutes. Let's move on to the falling states. From falling to rising, is rising must be true. From falling to grounded, the mover must be grounded and not being the ground is too steep. Falling to sliding would be that we are on the ground, but the ground is too steep. Sliding to rising, is rising must be true. Sliding to falling, we can't be grounded. Sliding to grounded is that we are grounded, but the ground is not too steep. Rising to grounded, we have to be grounded, but not the ground is too steep. Rising to sliding, very similar, is grounded, but the ground is too steep. Rising to falling, is falling must be true. In a little bit here, we'll add some jumping transitions, but that's really it. That's our whole state machine, and we'll start the state machine in the state of falling. Let's come all the way back up to the top of this class where we had commented out the setup state machine method. I'm going to enable that method again. The state machine has a method update, which processes all of the transitions. Let's call that during our update. Later on, I'll add the fixed update one as well. They're not doing anything right now, so it's not really critical. Anyway, that's as far as we need to go to be able to run another little test here. So let's jump back into Unity. There's only one thing I want to do before I press play, and that's because we're handling friction, ground and air friction inside the player controller. So I've made a physics material here called no friction, and I'm going to add this physics material to the capsule collider on our hero. Let's take a look at it quick. You can see it has absolutely no settings and the minimum amount of friction. This will just make sure that all of our sliding and moving around the ground is exactly the way that we've coded it. I'm also just going to bump up the step height ratio just a little bit because I know it's more suitable for this character. So let's hit play and just move around. Now we don't have any camera controls yet and we can't jump, but check it out. We can go upstairs, no problem. That's looking pretty good. We can handle a few bumps on the road. Let's try these little stairs. Yeah, that works good. Fall back down to the ground. I mean, it's a pretty minimal little test here. Once we get jumping in, we'll really be able to move around in the zone. Let's jump back into code. This isn't going to take very much to implement jumping now. I mentioned earlier that we could call the state machine fixed update method within our own fixed update method here. It's not really necessary, but let's add that for completeness. Now let's focus up on the start method. Right after we enable our player actions, we might as well just listen to the jump event. Then we can add a new method, handle jump key input, anytime that event fires. The jump key is pressed variable represents whether the jump key is actively being held down by the player. So if that's false, but the event tells us that the button is being pressed, we're going to set the jump key was pressed variable to be true. Was pressed represents the fact that we've pressed the button since the last time we reset all of our button states. Now, let's suppose that our jump key is pressed, but we get the event saying that it's false. Well, then we can set jump key was let go to be true, and the jump input key is locked to be false, meaning we can start another jump. Now that we're through our button logic, we can toggle the jump key is pressed variable based on the value we got from the event. Now let's scroll all the way down to our handle momentum method. Here we left a comment to do handle jumping. Now remember, we already have a state transition from grounded into the jumping state based on those booleans we just set. Here in our handle momentum method, we can say if our current state is the jumping state, well, we can handle our jumping. So right underneath this method, let's add a new method for handle jumping. This is going to be super straightforward. All we're going to do is first use the vectormath.remove.vector method to actually eliminate any vertical movement at all. And then we're going to replace that with our own by adding tr.up multiplied by our jump speed to our existing momentum. Now we have a lot of state transitions that are related to jumping. Let's write a few methods that we can call when we're entering our states so that we can properly handle leaving ground and touching ground again. So we'll have a method we can call when we start a jump. We'll have a method we can call whenever we've lost ground, whether we're falling or anything like that. And we'll have another one that we can call when we touch down again. Now, touching down on land is going to be the simplest because all we really want to do here is fire off the on land event. Let's get our collision velocity, which is really just our momentum, and we'll pass that into the event. So we'll invoke the on land event, and that's it. Our animator or our VFX or anything that's listening to that will get the message along with our current momentum. So next, let's handle on ground contact lost. First, let's do our normal momentum conversion. Next, let's get our current movement velocity. Now, this is actually our saved movement velocity that we've saved during our fixed update. But let's make a public getter for it because we're going to need it or potentially need it for other things as well. I know I'm going to need it for my animator controller. So next, let's say that if both the velocity and the momentum are non-zero, we'll project momentum onto the direction of velocity to find the component of momentum aligned with the velocity direction. We'll calculate the dot product between the normalized projected momentum and the velocity to determine if they're in the same direction. If the projected momentum is greater than or equal to the magnitude of the velocity and the dot product is positive, we're going to set the velocity to 0. This will prevent additional acceleration in the same direction as the momentum. Otherwise, if the dot product is positive, let's subtract the projected momentum from the velocity to slow the player's movement in that direction. Then let's add the adjusted velocity to the momentum. This will update the overall movement vector of the player. We're all done now. So once again, let's make sure that momentum has been moved back to world space. Now, I know that's a lot of vector math to digest there, especially those two lines, the if and the else if. What we're doing there is we're saying if the momentum is already sufficient to bring the player to a halt in the air, then the velocity is set to 0, simulating an instant stop. If the momentum is still propelling the player forward, then we're going to reduce the player's velocity by the amount of momentum, and this will give us a proper jump speed in the air. Okay, last method, on jump start. Again, let's do the transformation, use local momentum. And what we can do here is we can just apply our jump speed to the transform.up vector, add that to our momentum. Next, we'll start the jump timer. Let's make sure we set our Boolean value, jump input is locked to be true, meaning that we can't initiate a new jump while this is happening. The last thing to do, fire off our on jump event, passing in the momentum. And that's it. Let's transform our momentum back to world space. So let's finally take a look at these states that I set up earlier behind the scenes. So every state has a reference to the player controller. We did that when we initialized them all. And I've commented out all the methods that we're going to use here. So when we enter the grounded state, we're going to call the on-ground contact regained method on the controller. The falling state actually has nothing to do, but the sliding state, actually, when we enter the sliding state, we're going to call the on-ground contact lost method. Now I'll just page down here so we can see the other ones. In the rising state, when we enter the rising state, we're going to call the on-ground contact lost method. And when we enter the jumping state, we're going to call two methods, on-ground contact lost and on-jump start. Okay, we're almost finished. Let's jump back to the player controller for just a couple more things. We're using Boolean values to track our key presses for the jumps. Let's make sure that we reset the ones that are retaining state. So jump key was let go equals false. Jump key was pressed equals false. Now we can call this reset jump keys method during our fixed update right at the very end. Now I have one more transition I want to add to our state machine. So let's go back to our setup state machine method. I had left a comment in there. I'm just going to expand this again and we'll find it right at the bottom. So here I want to say that if we're at the jumping state, I want to move to the rising state as long as either the jump timer is finished or the jump key was let go. This will let us end the jump either when the duration is over or as soon as the player lets go of the key. Now I'm going to repurpose this comment because we need to actually add one more transition, and that's when we hit the ceiling, if we add the ceiling detector. So we'll come back to this later. Now, I made one mistake while I was recording earlier, and that was that I was calculating the momentum changes for sliding to the entire momentum within this handle sliding method. That's actually not quite correct because we haven't combined our horizontal momentum and vertical momentum together yet. So I'm going to jump back up to the handle momentum method. We'll apply these changes to the momentum as a final calculation in that handle momentum method instead, after the horizontal and vertical momentums have been combined together again. Okay, well, why don't we test out our jumping and make sure that that's correct? I'm just going to hit play here. And yeah, we can jump up and down, no problem. Movement still seems fine. Let's see if we can jump and land on terrain. Yeah, that's great. Moving up and down. It's great. Can move forward. We've got a little bit of momentum applied that way. Now, if I come out of here and change the jump duration to be 1, I should be able to hold the button down for at least 1 second. And yeah, there we go. I can let go of it at any time and stop the jump though. It's exactly what we wanted. So next week, we're going to cover the camera controller and the camera raycaster that'll look for obstacles between the camera and the hero. And we're going to deal with the turning. We'll add an animation controller so you can get the animations that we're seeing here for running and jumping and whatnot. It'll be a little bit of a shorter video and certainly not as intense on the vector mathematics. And of course, because this is going to be a 2-part video, if you have questions about this video, maybe I'll be able to address them in next week's video as well. So feel free to post those in the comments below. I want to add as well that even though I wasn't able to record the camera stuff, the code is written and I'm going to put it in the repository. So if you want to get a head start on next week, or you're just curious what it's all about, feel free to go and have a look at that. Hit the bell if you want to get a notification for next week's video. Maybe I'll see you there.